All right. Let's get started. All right. Settle down. All right. All right. Settle down. Guys. All right. Let's get started. A couple quick announcements on some things. So first off, you all know that your homework 5 is due on Thursday. This is the last chance in lecture to ask any questions about it. Does anybody have any questions about that homework assignment?
I have one. So does the rule still stand that we have to turn them all in on individual sheets of paper?
On this one, I could see where that's not a big deal, so I'm not worried about it on this one because it is pretty short. So no worries on that. Yeah.
I've been saving paper all semester.
You haven't been doing that?
I have our docs and
I guess the TA hasn't been.
Uh-oh.
Okay. Why did we just load it?
Oh, look. I'm not going back. I'm not going back. I won't do that. I'll just going forward. And I'll say this. That rule isn't as big of a deal on assignments where the problems are particularly short, but I'll just say this. Okay, so next semester, many of you will probably be taking concrete design, and those problems get long. They really do. So you kind of need to separate them. So, but we'll just move forward. I'm not going to go back. Don't worry. Yeah.
Well, those usually take like.
It's supposed to independent bodies as well.
Okay. All right. We'll move past it. A couple things. I do need to bring up something on lab. So this Thursday, we were supposed to do our steel and alloy tension testing lab. We were supposed to do that in 2 days, but there's a little bit of a back order on the specimens that we're testing. It's not like concrete or aggregates where we can create our own specimens that easily. I mean, you have to sort of order them, or you have to machine them. And long and short of it is, I'm going to put that lab off a week. So that is going to make our exam day maybe a little bit longer, but the nice thing is we're only doing one set of cylinder tests that day, so it should shorten that lab a little bit. And plus, this lab, the steel and alloy lab next Thursday is fairly short in and of itself. I mean, you're observing the test, you're getting the data, and then that's it. It's pretty straightforward. So that'll be pretty straightforward. Everybody okay with that? Okay. So just so everybody's clear, next Tuesday we're having our exam review, and then we're having our exam next Thursday on cement and concrete. Okay. So everything past exam 1 and up until now, that's exam 2. Everybody okay with that? So on Tuesday, make sure that you come prepared to ask questions. Make sure that you've got, homework. If you got any homework questions, any lab questions, anything like that, come ready next Tuesday. So come ready on Halloween for questions. One other thing, on Thursday, bring your data sheets from the cylinder tests from last week. If you go through your final report guidelines for the Portland cement test, or the Portland cement concrete test, not only do you have to analyze your data, but you have to analyze everybody else's, okay? So we need to start collating that data, so I'm going to ask you to bring those data sheets next week. And what I'll do is I'll collect compressive strength data from all of the groups, and I'll post it on Blackboard so that you all will have that data available. See, for each individual group, you're going to have to go through and do the gamut of, averaging your diameters and lengths and all that, and sigma equals P over A to get your compressive stress. For analyzing everybody else's data, I'm just going to give you the compressive strengths, and then you all can graph it and compare. So everybody okay with that? So again, on Thursday, make sure you have your data sheets. Sound good? Okay, so today, I guess today sort of marks the final chapter, if you will, in this course. I mean, we've been, from day one, we've really been spending the majority of the semester towards one achievable goal, and that's assessing concrete. I mean, what we did with aggregates, what we did with cement, and what we did with PCC was all really geared towards understanding how to proportion a concrete mix design. That was really one of the big goals of this course, and we have since completed that. Now what I want to do is cover some other very important civil engineering materials that are sort of independent. They're sort of on their own. Like we'll cover steel, and then we're done. We'll cover aluminum, then we're done, and so on and so forth. So our first sort of material that's on its own that we're going to cover is steel. So I want to talk about steel from a material aspect. I want to talk about its advantages, disadvantages. I want to talk about a little bit of its history, how we produce steel, what steel products are out there that we use as civil engineers, and understanding some fundamental properties. Yes? No. This is final. Yeah, this is the final exam. This is exam 3. Now, you will be examined on it, just not in a week. So, okay. So let's talk a little bit about steel. Steel, I mean, regardless of what type of work that you all do when you get out of here, if you're working in the engineering discipline, you're going to interact with steel in some fashion or another. Even if you're somebody who focuses on reinforced concrete, well, it's reinforced concrete. What do we put in concrete to reinforce it? We put steel, okay? Now, one of the things that's a little different about how we're going to assess steel in this course, and it's one of the reasons why steel and wood and aluminum and all this stuff is saved for the end. We as engineers and as civil engineers, we assess steel a little differently. When it comes to concrete, we actually have the ability to design a batch of concrete to achieve a certain compressive strength. We have the ability to control how much gravel and sand and water and Portland cement and admixtures go into a given batch of concrete in order to achieve desired outcomes. That's most of the time that's really not the case with steel. With steel, we're just saying, here's the product, here's the properties, and that's it. There's not really much ability for most civil engineers and structural engineers to actually start specifying, the chemistry of steel, for a given outcome. Usually we're just saying, here's my building, here's the beam I need a W 27 by 84, here's the properties, okay, go with it. And for those of you who have already had steel design, you'll remember that's kind of how we approached it in that course as well. We had a member, here was the properties, go. So the way, what I expect you all to understand and what I expect you to know is going to be a little different. Now, let me not cheapen the topics that we're going to discuss just because we as civil engineers really don't specify, the alloying agents and the chemistry of a given mixture of steel. That doesn't mean we don't need to understand it. So there are going to be some fundamental properties of steel that I want you to understand. And if you take steel design, if you choose to take steel, we'll explore some of this stuff in much greater detail in there. I do want to discuss some advantages of steel. And we can talk about disadvantages, but a lot of these disadvantages with appropriate engineering can be overcome. So one of the biggest advantages of using steel is its strength and its stiffness. If you just look at the fundamental properties of steel and compare it to something like concrete, steel members have, they give you more bang for your buck, if you will, in terms of strength and stiffness. For instance, if you just look at yield stress, y'all remember what yield stress is. That's the point at which we start to experience permanent deformations in a particular element. Well, if we're talking about just regular old grade A36 steel, I mean, we're talking about yield stresses that are 36,000 psi. Compare that to compressive strengths in concrete where it's only 4,000 psi. So we can achieve much larger stresses and capacities with steel. Steel also possesses a higher degree of stiffness, okay? So, for instance, if you look at the Young's modulus for concrete is usually around 4,000 KSI, 5,000 KSI, something like that. What's the Young's modulus for steel? My folks who've already had steel design. 29,000 KSI. That's a number I want burned into your memory by the time you get out of here. It's like 62.4 pounds per cubic foot. It's one of those numbers that just should be in here. You know, hopefully by now we know what 62.4 pounds per cubic foot is, right?
Get out.
Yeah. See, I came up with a structural engineering way of saying, like, get out. Say, well, how about this? When you subject a free hinge to a moment, or subject a hinge to a moment, it results in free rotation. Try it out. Do you like that?
Who's got the Twitter?
Now, one of the things, one of the other advantages of steel is its uniformity. You know, unlike concrete, where with concrete you have to deal with shrinkage and variable moisture contents and things like that, steel properties really don't appreciably change with time, or at least and as much as elements like concrete can. So properly maintained, and I say properly maintained because this can be a disadvantage, properly maintained steel structures can last almost indefinitely. So one of the disadvantages of steel is that in exterior applications, what does steel like to do? It likes to corrode, it likes to rust, and that can create a significant problem with steel's performance over time. So you do have to provide corrosion resistance, either by painting elements in the field. I am not a fan of painting bridges. Don't do it. Either galvanize or use weathering steel. Painting, you just have to keep painting it over and over and over again. It becomes a maintenance nightmare. But it is something you have to assess, especially in bridge scenarios. With bridges, anybody who's ever worked, any of you all who's ever had a summer internship with the DOH and gone and done bridge inspections and seen bridge joints that have leaked or gotten a bunch of debris in them, all that moisture collection just goes straight to the girders and it causes a lot of corrosion issues. So it's something you have to keep in mind. Steel is also a material that is quite ductile. It has the ability to withstand large amounts of permanent deformations, and that can be important under certain scenarios. For instance, if you're ever designing a structure to withstand earthquake loads or earthquake accelerations, in an earthquake, buildings can be subjected to very large permanent deformations. And a lot of times, you know, in the world of earthquake engineering, we're just designing the building to make sure that it can stand after an earthquake. I mean, some of the forces are so ridiculous that there's no way that the bridge or the building could resist those loads and in the end even still be usable. I mean, another way of putting that, we actually in certain earthquake systems we actually designed certain elements whose sole purpose is to fail in order to absorb all that energy. So it's one of the advantages. One of the downsides is that some of those fabrication details and some of those connections can get a little pricey. So there's a little bit of a trade-off. I would also be remiss if I didn't mention steel's sustainability. Nowadays, and this is particularly true in the construction market, we're not melting iron ore and coke and limestone and whatnot to create new steel as much as we're melting old steel, melting old scrap to produce new products. And in the construction industry, this is very prominent. Nowadays, in the United States, most of the structural steel that we produce, and by structural steel I mean beams and columns and angles and wide flanges and plates and whatnot, most of that is produced through recycled scrap. And if you have a building that you're tearing down, I mean, you can recycle just about all of that steel into new products. Now, I say this about the construction industry. To be fair, most of the steel that we use in this country is not used in the construction industry. Take a wild guess where most of the steel goes in this country. The automotive industry, yeah. So most of the steel that we produce in this country goes towards the automotive industry. But at least in the construction industry, we're really starting to move towards sustainability with steel. I mean, we mined the heck out of it back in the day, why don't we just keep remelting it and reusing it? And steel is one of those products that works very well in that regard. Yes. That's a good question, and surprisingly, the answer is usually not. So what ends up happening is this, and we'll talk about production methods here in a little bit. Regardless of whether or not you're taking raw iron ore or melted scrap, your first process or your first step in producing steel is essentially to try and get that molten iron product. Okay. Once you've got that, your second step is to adjust the chemistry of that molten product until you achieve a target chemistry design for a given steel alloy. That process is just a little different, depending upon whether you're melting, raw iron ore or melting scrap. But in the end, once you start casting, regardless of if you're melting old scrap or you're melting brand new steel, it's still steel once you begin casting. Does that make sense? And a lot of, one of the other aspects of, or one of the other benefits of using scrap as opposed to raw iron ore is, you've got raw iron ore and coke and limestone, which comprise the bulk of what is steel. But dependent upon your steel grade, you're throwing in different alloying agents, vanadium or different there's a whole list of alloying elements, titanium, and so on and so forth. You end up having to throw a little bit less in scrap mixes as opposed to iron ore because a lot of those elements are already there. So we get a little bit of an advantage in that regard as well. Does that make sense? Everybody else okay with that? Good. All right. No. Okay. My remote has got a delay on it. There we go. So let's talk about steel, like when it was used. I'm not going to get back, go back to the Iron Age, back in history, but really steel is a somewhat modern structural material when you consider the use of it throughout time. It really didn't start to get major use until the 1900s. Back in the 1800s, it started to see some sporadic uses here and there. In Europe, there was a rail station in Paris where some of the I-beams were fabricated using wrought iron, and in 1851 there was an exhibit at the London exhibition that used steel products for load-resisting elements. You really didn't start to see major use of steel. Let me go back a little bit. You actually don't really start to see major use of steel until the 1900s because of a very significant invention. See, one of the advantages of steel is that steel will afford you the ability to build taller, okay? And you go to New York and Chicago throughout the 1900s, there was a big race to build, the tallest building on the planet. And that kept hopping around throughout the 1900s. But there was a point when there was really no point in building a taller building without one key invention. What do you think that invention was? What's that? The elevator. Why build a 50-story building with just stairs, right? So, in 1889, the first elevator for vertical transportation was installed and operated. Up until then, we really weren't building very tall buildings. Anybody want to walk up 30 stories, get to their office? No. So it really, what you find is that once the elevator was invented, buildings, if you start tracking, tallest building on the planet, it started, that's when the race started, is when elevators began. In 1889, in the same year, the construction of this there's this thing in Paris called the Eiffel Tower. I don't know if anybody's heard of that. Funny, what's that? Yeah. What's that? Yeah. I can tell you what it is. There's this dork right there standing looking at it. I don't know who that guy is. I gotta say, actually, yeah, I know, he's a dork. I gotta say this, actually seeing the Eiffel Tower up close, it's amazing, honestly, the level of detail, the level of intricacy. not to knock on the Leaning Tower of Pisa, but I've seen the Leaning Tower of Pisa as well. And when I saw the Leaning Tower, my first reaction was, that's short. I mean, honestly, the Leaning Tower isn't that tall. I mean, it's there, and I mean, you can't miss it, but it really isn't that tall. This thing is huge. And just being there and seeing the scale of it, it's amazing. And one of the things that's kind of funny is that when it was first getting constructed and it was first getting, installed, the French hated it. They thought it was an eyesore. They couldn't stand it. They just thought it was a big monstrosity in the middle of the city. Now it's the symbol of France. So I just find that kind of interesting. But the level of detail and the level of intricacy in this structure it's amazing. And if you ever get the chance to go see it, go see it. It's well worth it. It's a really cool site. I also recommend that. What's that? Yeah. I'm glad you said that. Now I'm doing a truss analysis problem in structural analysis. It's his fault. Oh goodness. I'll say this: if you ever want to go, I highly recommend going to check it out. Just also as a piece of advice, if you actually want to go up the elevator at the top, I recommend booking it well in advance, and I recommend picking the first slot of the day. Don't go at noon or 1 or 2. Go to the very first slot in the day. The reason why is because the way that the system works, once you go up there, you can stay up there as long as you want. So if you're the first group up on the elevator, you have a lot of room and you can check stuff out. Once the second and third group comes up, nobody wants to leave because they're on top of the Eiffel Tower and it gets pretty crowded. So if you want to enjoy the view, be the first one up there. So that's a random piece of advice, but it's well worth it. And also, it's just also a general piece of advice. If you have the chance to travel, do it. It's well worth it. Okay. What's that? Field trip to Paris. Yeah. Oh, okay. All right. Like I said, past 1889, once the elevator was invented and installed and proven to be a successful technology, then you started to see the skyscraper race, if you will. The Flatiron Building, the Empire State Building. You can see, the records just keep getting beat over and over again. This is an image. This is just an example. This is an image of the Flatiron Building in New York. Oh, lost my battery case. But yeah, you can see. I mean, you can just follow it over time. It's kind of an interesting, application. And then, from there, you can see the modern use of steel all around. Yes, sir. Oh God. Production of structural steel. Okay. There are two main methods. I'm just going to start reading the slide at this point. All right. Like I said, and I've kind of hit on this before, there are two main methods used to produce structural steel. You're either melting down raw components or you're melting down scrap and recycled steel. I've got a couple videos. I'm not going to watch both of them. How many of you all have seen how it's made or watch how it's made? You're an engineer. Of course you've seen how it's made. All right. This is how it's made on steel, and you can see in this example, they're actually melting old steel to produce new steel. I want to show you this one. The basic oxygen furnace approach, it's essentially the same idea where you're melting down raw components. Let me see if I can get this pulled up. So I think it's about right here. Okay, can everybody hear that? Well, not now because I paused it. Is that good?
The next step is the steelmaking process, where impurities are eliminated from the molten iron to produce crude steel. The molten iron created in the blast furnace contains various impurities that diminishes its strength and durability once it is hardened to steel. Therefore, a process of removing the impurities while the molten iron is in liquid form is necessary. The molten iron from the blast furnace is transported into a torpedo car and poured into a converter furnace. In the converter furnace, pure oxygen is added to burn off substances such as carbon, phosphorus, and sulfur to create purified molten steel. At this point, the temperature and substance composition of the molten steel is precisely adjusted according to the customer's various demands. Pouring the molten steel into molds and cooling it into solid steel creates a semi-finished material, ready to be made into finished steel products. The solid steel is categorized depending on its shape. Slabs are wide and flat, blooms are rectangular bars, and billets are thinner square bars. The final stage of producing steel is the continuous casting process, where steel is forged into various steel products. When a slab is heated above 1,100 degrees Celsius and passed between rollers, it turns into a thin and long steel sheet. This hot-rolled product is used widely as construction materials and pipes in various industries. Cold-rolled products, which are created by making hot-rolled products thinner at room temperature, are used in general appliances, barrels, and automobile frames. Coated steel, which is created by coating cold-rolled products with zinc, is used in high-end appliances, office equipment, and automobile exteriors. Electrical steel plates, which improves electromagnetic properties by adding silicon during the steel manufacturing process, are used in transformers and motors. Steel plates, which are thick and rectangular in shape, are used in large structures such as buildings, vessels, and oil pipelines. When a billet is heated over 1,000 degrees Celsius and passed through a roll with a round hole, it turns into a thin and long wire rod, which is used as automobile tire cords, wires for bridges, piano strings, and underwater cables. At the stainless steel plants, which is equipped with additional production.
We don't really use stainless steel, so in civil engineering, so I'm going to move past that. So, okay, all right. So what I showed you all was essentially a basic oxygen furnace approach. The electric arc furnace approach is basically the same thing, other than A, you're melting scrap, and B, it's a little bit of a different process to generate the required heat to melt the steel, but in the end, you're getting the same molten product at the end. So in terms of the general process associated with producing steel, I'm going to talk to you a little bit about the standard process where you're taking raw iron ore, you're taking coke, and you're taking limestone to actually produce steel. I do want to cover that a little bit because if you understand that, then you'll understand the modern process where you're just melting scrap. You can just sort of skip all of that. Now, in general, like I said, it's a three-step process. So we take our raw iron ore that has been mined and we convert that to what is called pig iron, okay? Now, pig iron is basically, it's kind of like near steel. It just has a pretty high carbon content. So the second step is to refine that pig iron into an actual steel, alloy. And then the final step is to form that molten steel into a product, be it a plate, a bar, rebar, angles, wide flanges, etc. So in step one, what you're doing is you're essentially heating that iron ore into a molten state, and you're adding coke and limestone. Now, what the coke does is the coke provides carbon into the mixture, and what that does is it helps reduce the iron oxide that's present in the mix. Now, iron oxide, anybody have another name for iron oxide? It's rust, yeah. So we obviously do not want that in our finished product. So what the coke does is it helps, it provides the carbon to reduce that in our mix. What limestone does is it bonds with a lot of the impurities that are present in steel. What happens is a lot of those impurities, once they bond with the limestone, they float to the top. Okay. So what we do is we skim off that top portion of that molten mix. That top portion, which contains all those impurities, is what we call slag. For the steelmaking process, we skim that off and then discard it, and then the rest of the molten iron and that carbon then goes on to be produced as steel. Now, That mixture, again, is what's called pig iron. Now, pig iron basically is about 90 to 94, 95% iron. There's a fairly high carbon content present in pig iron. It's about 4%. That is way too big for structural steel. The more carbon content that's present in your steel, the less ductile your steel is. And for structural steel, we need a significant higher degree of ductility. So this is way too high for structural steel, but it's okay for cast iron applications, like if you've got a cast iron motor or something like that, that's fine, because you're not going to, or you're hopefully not going to experience as many permanent deformations in those scenarios. So like I said, 4% carbon, way too high. For structural steel, we're in the 0.1 to 0.3% range, so we're going to have to reduce this a fair amount to turn this into structural steel. So that's what step 2 is. Step 2 is basically taking that molten mix and turning that or converting that into what's called a ladle metallurgy furnace. And the idea with this ladle metallurgy furnace is this is where you can introduce different alloying agents, titanium, manganese, vanadium, and so on and so forth to turn your molten steel into a grade that's for your given use. And let me be clear. I mean, there are oodles and oodles of grades of steel. I mean, there's thousands and thousands of different grades for all sorts of different applications. You're going to have different steel alloys used for tools, and as you are in the automotive industry, or in the aircraft industry, or in the medical industry, or so on and so forth. There's thousands of different grades in the civil engineering and structural engineering industry. I have here on a slide that there's really only about 200 of those grades that we as civil or structural engineers care about. But honestly, in practice, I would say it's a whole lot less than that. If you're a structural engineer and you are designing steel frames and beams and columns and connections in buildings, you're only going to deal with half a dozen grades probably throughout your entire career. Either, grade 36 or grade 50, the grades that are associated with bolts and fasteners. That's about it. Most often, or maybe grade 70 here and then, and that's about it. So just something to be aware of is that there's a host of different grades and applications out there. In this stage, like I said, we are trying to alter the chemistry of the molten state in order to get a chemistry that we need for our given application. You'll see a lot of times if you go to a steel mill, you'll see a worker who actually draws a molten sample from that furnace. I don't want that job because we're talking about molten steel. If you ever see them draw that, it's pretty intense. But ultimately, when we produce steel, we're trying to reduce our carbon, and we're trying to control, for the most part, undesirable elements. In other words, phosphorus, silicon, sulfur, and manganese. In certain quantities, those ingredients are fine, but we do try and control those for a given alloy. Okay. There are numerous different alloying agents that are available to us as engineers to actually control the metallurgy of a given alloy of steel. I mean, let me be clear. This is not a metallurgy class, and I'm not going to try and teach you metallurgy. You can get a whole degree, a college degree in just that. I just want to give you some general overarching associated info associated with alloying agents. But the different alloying agents that are available to us each have specific purposes. We try and control things like corrosion resistance, things like machinability, hardness, which can be important for like tool steels. Weldability is also an important characteristic of a steel. We want steel to accept welds in appropriate scenarios, and so on and so forth. So these are some common alloying agents that are available to us, and each of them have an intended purpose. So for instance, if you add nickel to a given alloy of steel, it's going to increase hardenability and increase toughness. So given your alloy, that might be more important. What about if you need to promote grain refinement, maybe add some molybdenum, and so on and so forth. And like I said, this is where specifications come into play. And like I said, there's hundreds and thousands of different steel alloys and steel grades for different applications, and those specifications control the chemistry of a given mix. So this is just to give you kind of an idea of the different alloying agents that are out there. Like I said, more modern, and it actually makes our lives a lot easier. Yes? Grain refinement, that's a good question. Grain refinement is essentially trying to control the microstructure of the steel. And this is, I don't want to turn this into a chemistry or into a crystallography lecture, but the idea is that if you look at a bond of steel, we're talking about at the chemistry level, getting into that microscopic level, you essentially have a grid structure of bonds of iron and carbon and so on and so forth. And that's trying to promote the uniformity of that structure, which can be important in like micro applications. Things like if here's a good example. In the aircraft industry, okay, if we use steel, it's really strong, but it's also really heavy. Okay, so there's a real push to use the thinnest elements possible. But if you've got a really thin element, that thin element has got to behave the way that you want it to. You see what I mean? Also in the medical industry, you can see that that being important. I mean, it's important for us, but not as much. We're not operating at that scale. So, everybody okay with that? That's a good question. Any others? I mean, this is good stuff. Okay. Like I said, the more modern method involves just melting scrap. It makes our lives a little easier from a chemistry standpoint, because if all you're doing is melting old beams and columns into new beams and columns, it's usually a little easier to adjust your chemistry. I visited what's called a mini mill. They're calling them mini mills nowadays, although they're not very many. They're like about a mile long. But I visited a mini mill operation in Iowa once where they were, it was that operation that I mentioned where they're melting old scrap in order to produce new steel. I mean, this place is a mile or over a mile long, and they're producing large quantities of steel. And as we walked in to see the ladle, the metallurgy furnace, and the where they were starting to adjust the chemistry, we walked past these bays that had their various alloying agents, like the bay, where the sulfur was, and where the vanadium was, and where the manganese. And they were very small piles. They actually didn't need very much because the scrap they were using pretty much already had attained the chemistry that they needed. So for this massive operation, I mean, you understand they're producing tons and tons of steel a day, and their pile of, I think it was vanadium, for the entire operation was no bigger than a car. Like, that's it for the entire operation. I just thought that was really amazing when I saw that, because I saw it, like, what's that? Oh, that's the vanadium for the ladle metallurgy. So, that's it? Yeah, that's all we need. I just thought that was amazing. So I just thought they'd need a lot more. Okay, any questions? All right. So once you've got molten steel, regardless of whether or not you're melting new scrap or you're melting raw steel, once you've got it molten, you've got to cast it. Okay, and there's really two main ways of casting it. You can either cast it in one large mass and then form that mass into an intended product. We call that ingot casting. In civil engineering and structural engineering, what is usually more common is to do what's called continuous casting. And instead of casting one large mass, you're essentially producing one long continuous either strip or slab or billet or plate or so on and so forth. And the idea is that you would produce what's called a near net shape, either like you saw in the video, a slab, a bloom, a billet, or something like that. And then through successive rolling, essentially slowly roll that into a desired shape. So, so once you've got your billet or your slab or so on and so forth, you can take that and then through successive rolling, convert that into a shape. And by rolling, what I mean is this. You're essentially taking this molten or this semi-molten shape, either a bloom or billet or something like that, and essentially passing it back and forth through hydraulically pressurized wheels. And what those wheels are doing, they essentially pushing on, you know, the molten shape and turning it into an I-beam or a channel, an angle, you know, a plate, a bar, what have you. If you ever see a rolling operation, it's very steamy. It's pretty intense, but you can kind of see it right here. This is a really good image of it. So here you can see this red hot billet that's being passed through a given roller. And look right here, you can see before and see after. See how it got smaller? You can see that it's slowly being turned into the desired product at the end. From an automation, from a factory standpoint, more often than not, most mills are designed and operated such that to go from near net shape to final product usually is done in an odd number of rolls. Because if you think about this like it's a factory or like it's an automated process, you have some product, right? Let's say you rolled it an even number of times. So it's going from, you know, left to right. So roll it once, twice, 3, and if we roll it 4 times, it's going to go back this way. So typically we try and engineer that so when we're rolling it an odd number of times so that it can go forward. So just a, you know, random factoid for the steel production process is that when you roll, you typically roll an odd number of times. Yes?
Because their work hardening doesn't typically take effect until after it drops below the point magnet.
Work hardening?
Yeah, like when it drops into the magnetic point, then you can work harden when it passes through the rollers.
True, but that usually isn't the biggest deal for us from a structural engineering standpoint. What we're more interested in from structural engineering are 2 things. My steel design folks are going to know all about this. Okay, number 1, and if you want to learn more about this, we talk about this in steel design all the time. But when you take, let's say, molten shape and convert it into a finished, let's say, I-beam or so on and so forth. Okay, when you do that, 2 things happen. One of them is you actually lock in internal residual stresses. So, and the reason is because if you're looking at, let's say, an I shape, okay, the tips of that eye, if you will, like if here's the I shape, the tips are going to cool a little faster than, let's say, where the flange and the web come together. So the problem with that is that there are actually stresses already locked into the product from day one. Okay. Now, if you're taking an element and you're applying tension to it, that really doesn't matter too much because when we design for tension, we assume we just blow through that. Okay. But in compression, it's a big deal because things in compression like to do something that things in tension don't like to. And what do things in compression like to do? They like to buckle. Okay. So under stability assessments, when you're assessing buckling, that's a big deal. Now that's the first thing that can happen. The second thing that can happen is you can have geometric imperfections. Not you can have, you always have geometric imperfections. What I mean by that is there is nothing on this planet that's perfectly straight or perfectly plumb. These shapes, when they're produced, I guarantee you they're going to have a little bit of a kink in it or a little bit of a wave in it. Under compression, that's going to be a lot worse. Okay. Under tension, again, doesn't matter because it's not a stability issue. So from a structural engineering standpoint, that's really more what we're interested in. Does that kind of make sense? Yeah. One thing I am sort of light on this lecture. I really don't get into heat treatment too much, like annealing and tempering and whatnot. It's important, but not really so much from a civil engineering or structural engineer standpoint. It sounds bad, but we really don't care. I honestly, as long as our product is meeting the appropriate specification, it really doesn't bother us so much. The only thing that I will mention is that from a workability is probably the wrong word, but from a workability standpoint, before the rolling operation, we do apply a little bit of extra heat to get the steel into a more workable fashion, into a more malleable fashion, if that makes any sense. Sound good? As far as I know, they do, and I know they also melt old scrap. I actually haven't been through a tour of that particular steel mill, so.
They have an electric blast furnace over there.
Yeah, I know they have electric arcs, yeah, so.
Yeah, they go from start to finish.
So it's continuous line. One thing I know, they're not producing like W36 by 135s. They're producing small, plates and small bars, smaller. I mean, I know it's a big mill, but it's compared to, mini mill or large scale operations, it's not a very big operation. So they're producing smaller products.
We have a constant extrusion. I worked over there on cooling.
Oh, okay.
We have a constant extrusion process, and they have a metal saw that chops it as it comes out and lays on the cooling bed.
Okay.
Then they straighten it, like you said, they make modifications to the structure.
Do they use an acetylene torch to cut the continuous cast into near net shapes, or is it?
They use a giant chop saw.
Really?
Yeah, so you always turn your heart rate around backwards so that the sparks don't go down your palm. Turn the hard way.
I know that in the continuous casting process, from a handling standpoint, you're either using a chop saw. Most large-scale operations just use an acetylene torch that just cuts that continuous cast, and then they lift it either for storage or into the reheat oven to begin the rolling. So yeah. Any other questions? This is good stuff. I like this stuff. Okay. All right. Let's talk a little bit about the produced products that you get from steel. There's a couple things that I want you all to know very well by the time you get out of this class. So what I want to talk a little bit are the products, and that's really what's going to matter more to us as civil engineers and as structural engineers. Let's start off by talking about steel grades. Now, steel grades are determined by their exhibited mechanical properties. What's their yield strength, what's their tensile strength, so on and so forth. Are steel grades determined by their Young's modulus? The answer is no. Young's modulus is constant for grades of steel. It's 29,000 KSI. Again, have that number drilled into your head by the time you get out of here. By the time you get your degree at Marshall, that'll be a number you remember. But steel grades are determined by their exhibited yield strength, their exhibited tensile strength. You'll hear me use the term tensile strength and ultimate strength interchangeably, but they mean the same thing. They also are determined by their exhibited elongation, how much ductility they are exhibiting. Steel grades are determined by mechanical properties and then also by their chemical composition. What's their percent carbon? What's the percentage of various alloying agents present in the mix? Now, I'm showing you this table. For those of you that have had steel design, this table should actually look somewhat familiar, or at least the left half of this table should look somewhat familiar. I'm going from the FU column all the way to the left. This is a table that, I know. Let's go ahead and get past it. I know. This table from here to the left, this is copy and paste right out of the steel manual. For those of you that have had steel design, you looked at this table every day in that class, because this is how we determine the design values for a given grade of steel. One of the things that's kind of interesting is, for instance, if you look at grade 36 steel, grade A36, this is one very common grade of steel that you see used in a lot of engineering applications. The yield stress is taken to be 36 KSI. So if you're in a design scenario and you want to ensure that this member does not yield, you limit its stress to 36 KSI. That's the idea. Okay? Now, its ultimate tensile stress, there's a range. It's 58 or 80. Now, the folks who've had steel design don't answer this question. Okay? If you're in a design scenario, what value do you use? Like if you're designing with A36 steel, what would you take as the ultimate tensile stress? 58. You take the worst case scenario, you assume the lower value. And then I'm sure somebody's sitting there going, why the heck do you put the range? Why don't you just tell us the 58? Why don't you make it simpler? Well, there's a good reason for why the range is present. Back in the late 70s and the early 80s, we as structural engineers were telling all the structural engineers and fabricators and so on and so forth that if you're designing in an earthquake zone, you need to be using moment frames. And what a moment frame is basically a frame that is meant to withstand lateral loads on buildings, and we designed that to withstand those lateral loads by using rigid connections between the beams and the columns. I might have mentioned this in this course before. I'm not 100%, but when you design buildings to withstand lateral loads, you actually don't design the entire building to do that. You only design a small subset of the building to do so. To give you an idea of what I mean by that, if you're in a car and you're in the passenger seat and your friend's driving and they don't know what the hell they're doing, and they're driving 50, 60 miles an hour and they hit the brakes, what's the first thing that you fling into? The seat belt. Wear your seat belt. Yeah, you steel folks have heard this before. But the idea is we don't design the entire car to hold you back. We install a system that specifically is designed to hold you back. We call that system a seat belt. The same thing is true in buildings. So like for instance, I think I left that over there. Hold on. Like I'm going to skip ahead a little bit. Okay, like right here. Okay, this is an image of a steel frame that's undergoing construction. And you notice you can see these inverted V's. We call those chevrons. That's what the shape is. But you see these chevron-type braces. They aren't everywhere in the building. They're only in these two bays that you can see right here. Those chevron braces that you see right there, they are designed to keep that whole building upright under a lateral load event. There are two lateral loads that, let me go back to here. There are two lateral loads that buildings need to be designed for, and that's wind and earthquakes. Back in the 80s, we were telling engineers to use moment frames in earthquake zones because moment frames exhibited perceived to exhibit far more ductility. Okay? Now here's the problem with that. 1994, Northridge earthquake happened, and what the structural engineering community found was a lot of structural steel moment frames out in earthquake zones were failing. Okay? The connections were failing. The reason why is because they were using grades of steel and they were assuming 58 KSI, but what they were actually getting were steel grades that were much higher. See, if you go buy a piece of A36 steel from the mill and you go test it in a lab, you're probably not going to get a yield stress of 36 KSI. You're probably going to get a yield stress of 40 or 50 KSI. This is the minimum, okay? What was happening for a lot of these grades is that they were assuming a yield stress of 58 KSI, or an ultimate tensile stress of 58 KSI, but they were getting upwards of 70 and 80. And you think, well, gosh, that's great. The steel was stronger than what they thought it was going to be. Well, the problem with that is stronger steel leads to steel that is less ductile. So because the steel wasn't behaving the way they thought it was failing under earthquake load. So if you want to know why the range is there, that's the range. I know it's a big, long answer, but there's no way to tell that shortly. So some of these you'll find pretty definitive yield stress. A lot of them you'll find ranges. Use the minimum. Okay. All right. Hot-rolled steel is generally produced in two main fashions. You're either producing something like plates or bar stock or something like that you can use to actually fabricate girders. How many DOH folks how many students have been in DOH projects? Okay, all right. If you look at steel bridges, most of your short bridges, I'd say 40, 50, 60 foot, you're using a rolled I-beam directly out of the mill. But if you're looking at, something like the Nitro St. Albans Bridge, some 12-foot deep girder, it's not fabricated using a rolled I-shape. They're actually taking plates and welding them together, tailoring those sizes to produce a given girder. And that's in civil engineering. That's one of the big applications of using steel plates. You're also obviously using it for connections and what have you. But you're either producing plates and bars or some type of rolled shape. Steel Manual actually provides you some pretty nifty guides on, depending upon your product that you're using, what grade of steel is most applicable. So for instance, if I buy an angle from a steel mill or from a service center or somewhere like that, more often than not, when I purchase that angle, it's going to be comprised of grade A36 steel. The same thing for C-shapes or channels. Same thing for HP. Those are piles. That's going to be in grade A36 steel. So if you ever look at a pile, it's probably A36. Wide flange shapes are usually produced in A992. Those are usually used as main load resisting elements in buildings and bridges. Okay, terminology. This isn't called the upper and lower flat piece on the I-beam. This is the flange. This is the web, okay? This is the leg of an angle, and I know, well, what's that one called? It's a leg too. So this is a leg of an angle, that's a flange, and that's a web. So just so everybody's aware from a terminology standpoint. Everybody good on that? Okay, all right. Okay, steel designations. I've been using the word I-beam a lot. We really don't produce I-beams anymore. Standard I shapes aren't really produced. The difference between a standard shape and a wide flange is that the standard shapes, the flanges, they kind of got a little thicker as you went in. Nowadays, the flanges are predominantly flat. If you ever hear the term, and I've got here a W21 by 93, I want you to understand what that means. Okay, so first off, the W. Okay, the W refers to what shape we're talking about. Is it a wide flange? If it was a channel, it would be a C. If it's an angle, it would be an L, so on and so forth. So if you ever hear W something, that's what the W is referring to, the shape classification. All right, the 21. The 21 refers to about how deep it is, and I'm using that term very specifically. Okay, 21 refers to the nominal depth. So this element would have a nominal depth of about 21 inches. If you look at all the W21 shapes that are produced across the country, you're going to find some variability in the depth. You know, one might have a design depth of 20.9, one might be 21.2, one might be 20.8, or so on and so forth. But because they're produced according to the same rolling schedule, they all tend to belong within the same family with an average nominal depth of 21. One of the things we talk about on day one in steel design is the difference between values that we use for design and values that we use for detailing. So a W21 by 93, if you're in design mode, you'd probably be using whatever the depth is listed in the manual. Maybe it's 21.2 or 21.3. So just so that you're aware of that. But the 21 is about how deep it is. The 93 is about how heavy it is. Okay? So a W21 by 93 would be a W shape that is about 21 inches deep and weighs 93 pounds per foot. That's what the 93 means. Okay? So obviously, you know, if I were to ask you what's a more economical shape, a W21 by 93 or a W18 by 40, the answer is the W18 by 40. It's lighter. All right. If it's lighter and you're buying steel at price, dollars per pound, well, the lightest shape rules. In fact, whenever you take steel, just about every problem that we do throughout that entire class, we're designing according to the most economical cross-section, and the most economical shape is the one that's lightest. So this is our way that we assess that. Everybody okay with that? All right. Now, angles, the terminology is a little different. So for instance, if you have an angle that's 6 by 4 by 1/2, it has, obviously the angle has two legs. The long leg is 6 inches long. The 4 is the short leg, so it's 4 inches long, and it's each leg is a 1/2 inch thick. If it was an equal leg angle, it'd be something like L 6 by 6 by 1/2, something like that. Yes. That's a good question, but from a rolling schedule, we never produce that. Now, it's possible that you could fabricate an element, like you could actually take a plate and a plate, but we wouldn't name it in that scenario. You'd name it whatever you want. So, but we from a rolling perspective, they're all the same thickness. So, good question. Everybody good? All right. Okay. Let me see what time it is. Okay. I'll go for a little bit longer, and I might end a little early. Okay. So, hot rolled steel products generally are used to produce much of the civil engineering applications that we experience in our career. So hot rolled steel products can be used for girders, for beams, for columns, for connections. Those are hot rolled products. There's also a pretty significant use of cold formed products. Now, a cold formed product is used by, is fabricated by actually taking a cold sheet of steel and actually successively bending it into a desired product. So typically what you'll see is a big, large flat piece of steel, and you'll see a series of successive rollers. And what those rollers will do is they'll take a flat piece of steel and through successive rolling, form it into a desired shape. So it might start out flat, and then the first roll kind of gets it started, and the second, the third, the fourth, and by the end, you can see we've achieved a desired outcome. Everybody in this room has actually already seen cold formed steel used at some point. How many of y'all have ever been to Sam's Club or somewhere like that? Those big stacks and those big columns where they're stacking the pallets of mayonnaise or something like that. But if you look, those big steel posts, those are cold formed steel shapes. Cold formed steel is becoming pretty popular in light gauge commercial construction. You'll see it used for deck pans in buildings. You'll see it used for studs, wall studs, and what have you. You get a lot of, by actually engaging in that cold form process, you can actually get a lot of increased strength. By increasing that strength, though, you do reduce a little bit of the ductility, which doesn't really matter if you're only going to use this for a light load resisting element. It's not that big of a deal. One of the disadvantages and one of the little trouble points associated with cold formed steel is that cold formed steel elements tend to be a lot thinner than hot rolled shapes, which can be good, but it can also lead to issues with buckling. Buckling of thin-walled shapes is a research area that's exploded here recently, and there's a lot of good work on just trying to determine how something like this buckles. It's not easy. It's a weird cross-section. It's got all sorts of different ways it wants to buckle. Also, if you've got a steel element that's really, really thin, it can be subjected to corrosion. So you have to make sure that it's being protected against moisture quite well. Everybody good so far? All right. This will be my last thing for today. I want to talk a little bit about fasteners. There are two types of fasteners, generally, that we use in structural engineering today. Bolts and welds, okay? What about rivets? We don't use them anymore, okay? Rivets are a more classical means of joining together steel elements, but they're time-consuming. They're a little unpredictable from a capacity standpoint, and they're a little more dangerous. I mean, you're having to heat this rivet up, to a substantial degree. I mean, it's dangerous. So we don't really use rivets anymore. With high-strength bolts and with welds and the procedures that we've developed nowadays for bolting and welding, we really don't need to go through all that hassle associated with riveting. It's simpler, and bolts and welds are simpler, and they're more predictable nowadays. So a little bit about bolts. So first off, if you ever see a structural bolt, you're going to see two things on the face of the bolt. The first thing that you're going to see, like for instance, if you're looking at this one, see where it says A490. A490 is the grade. So this would be an ASTM A490 bolt. This would be an ASTM A325 bolt. So this is the grade of the bolt. This symbol down here. Anybody guess what this symbol is? The folks who aren't in steel design or haven't had steel design. The manufacturer, exactly right. This would be a Lejeune bolt. I can't quite remember what that one is. A325 and A490 bolts tend to be the most common ones that we use. A325 bolts are much more common. A490s, they're a little pricier, but they're a little stronger. And this is where the trade-off of engineering comes into play. I mean, do you use 12 A325 bolts or do you use 8 A490s? Well, it depends on the price, and that can change from day to day. When we design bolted connections, we typically design them two ways, okay? One of our design philosophies is to design what's called a bearing type connection. And by bearing type connection, what I mean is, here is the hole that is in the plate, here is the bolt, and we are literally designing these assuming that the bolt comes into contact with the plate, and we ask ourselves, which one fails first? Does the bolt fracture or does the plate fail? Okay? And in steel design, we talk about this in very significant detail, but the long and short of it from a design philosophy is once you determine the capacity of a single bolt, you say, all right, here's how much load is on the connection, here's how much one bolt can hold up, divide, it'll tell you how many bolts you have. That's basically it. There are a number of detailing considerations you have to look into, like making sure the bolts aren't too close together or too far away from the edge, but that's essentially it. That's what a bearing type connection is. A slip critical connection assumes that actually takes into account the friction that's generated between your two surfaces. Let me ask you a question. If you have a plate and you have a plate and you bolt those together and you tighten that bolt, what are you doing to those two plates? You're pushing them together, right? All right. And you're going to take that connection and you're going to load it something like this, right? I'm going back to physics 211 and I'm thinking, well, if I have a normal force and I have a coefficient of static friction, I can determine how much force is required to fail that connection. Slip critical connections are very important in scenarios where you're subjected to fatigue. Let me ask you a question. What do you think would happen if you had a lawnmower and you had your mower or your engine or your motor bolted to the frame, but it was bolted very loosely? What do you think would happen? It'd fall off, right? Because under that cyclic loading scenario, under that cyclic loading, the bolted connections would not be very stable and the bolts would get loose and fall off. In bridges, in any type of scenario where you're going to be subjected to cyclic loading, we require slip critical connections. So if you take steel design, we do tend to look at both. Let me see what time it is. I'll tell you what. I think I'm actually going to call it for now. What we're going to do is this. Okay. So next time, I want to get back. I want to pick this up looking at connections. I want to look at structural fasteners, not only from a bolt standpoint, from a weld standpoint. I want to get into properties of steel. That is something that we're probably going to discuss either Thursday or the following Tuesday. But what I want to do, one of the other skills I want you all to have is, given data from a tensile test, I want you to be able to determine what is the Young's modulus, what is the yield stress, and so on and so forth. We'll discuss that stuff probably either next time or the week after. I do have to recognize that after Thursday, we're taking a break from steel because you all have a celebration coming up next week. So we'll figure out the healthy balance point, though. All right, that's all I got. I will see you all on Thursday.